Hello. So, my name's Graham Sutherland, and I work at Cisco, which is, well, I used to work at Portcullis, we got bought, so now Cisco. This will be my fourth talk at a Securi-Tay, so I've been to most of them now. And I'm going to talk about virtual machines and sandboxes. I apologise if anything weird happens to the slides because I'm running it in a VM and I can't actually see anything on my screen. So yeah, this is me. Worked at Portcullis for 3 years and now we got bought by Cisco, so technically I've only worked there for a short time now, but it's the same. My primary focus is mostly around like Windows stuff, binary applications, reverse engineering, weird protocols, digging into Windows internals. I like drivers and stuff. It's fun. I also like crypto and hardware and anything kind of weird. That's pretty much self-explanatory. We are expanding the team, so I think we're doing internships and stuff, so just come see us if you're interested in getting a job. And we're sponsoring the bar, so you can all get them for free. So, who recognises the term "Am I living in a box" as a song? Right, that's all the old people. So, just like me, they're a one-hit wonder. They were terrible. Yes, it was a band called Living in a Box, and they had a song called Living in a Box. But this presentation is not about them. It's about asking the question, as a piece of software, am I being watched? Am I being encapsulated inside some sort of container? So, am I running in a VM? Am I being debugged? Am I inside a sandbox? Am I running in an emulator? Are my calls being hooked? And most importantly, am I being watched? So it's mostly about malware, but not always. So, yeah, malware wants to be invisible. It doesn't want to be analysed, and that's important because obviously the bad guys want to do it. We want to understand how the bad guys do it. We kind of want to do it ourselves sometimes for red teaming stuff and certain other reasons, if you're a nation state. And we want to understand how virtualization and sandboxing and stuff works, because that's an interesting topic, I think. So there's been prior work. Sorry, you might not be able to read the bottom bit, I'll duck. But basically, there's been some prior work on this, both in terms of the attack and defense side, so identifying ways that malware hides from sandbox environments, hides from VMs, does weird things when it runs on a VM, so it looks like innocuous software. So you run the evil software, and instead on the analysis machine, instead of it getting pwned and sending all sorts of stuff over to sites in Russia or China or wherever, and instead what it will do, it'll go, here's Tetris, play that. And then the analyst gets confused and then plays Tetris for 4 hours because it's addictive. So yeah, there's some papers on it, there's been some talks on it a few times. I did a very brief talk on it. I think it was like 3 hours between coming up with the talk idea and doing the talk at DC 4420 in London. Lots of scattered information around, and I kind of want to just pile it into one place, which is this talk. And there's a guy at work as well who's done some analysis of this tool called Pathish, I think that's how you say it. Which is a VM identifier, so you run it and it says, I'm running in a VM, or it says, I'm not running in a VM. And working out how it does that is quite cool. Okay, so we're going to look into VM and emulator detection, we're going to look into sandboxes, we're going to look into some anti-debug stuff, mostly not going to cover anti-debug because it's been done to death. Some behavioural detection stuff, and offensive measures, so ways that you can mess with the analysts, and some potentially not so legal ways you can mess with the analysts, which I've certainly never done. So we'll talk about it, but we don't do it. So virtual machines are not real machines. They are a software abstraction of a real machine, which means that they're not the same, because you can't make a perfect clone of a piece of hardware. It's always going to be slightly different. So you can take something that's, you can take this laptop, and then you can run a VM, and the VM will always look different to the laptop that it was running on, because you can't physically make it identical. Like, you can't expose everything that's on the laptop, because then it's not the virtual machine anymore, that's just the laptop. Because that way, if you had two virtual machines running, they both would be running exactly the same hardware and talking to exactly the same peripherals at exactly the same time with no separation, and everything would go wrong and catch fire. So there's lots of ways to detect them. We can look at the hardware, we can look at the firmware, we can look at the software. So hardware, obviously things like disks, network cards, the physical processor, memory, things like that, the BIOS, the motherboard, the chipset, things like that. Firmware again, things like BIOS, UEFI, Intel Management Engine, trusted platform modules, things like identifier chips on memory called SPD. So if you can't talk to them and ask them questions and interrogate the firmware, then maybe it's a VM, or maybe you can talk to it and it's going to say weird things back because it's not a real piece of hardware. Or maybe it just looks like a weird piece of hardware. And also software, because a lot of the time when you set up a VM, you actually install a lot of stuff that you would just never install on a non-VM piece of machinery. So like, you're not going to put VMware guest services on your laptop unless it's running VMware, because it wouldn't work and it wouldn't do anything. So also analysis tools, because at the end of the day, it doesn't matter whether you're running a VM if you've got, you know, like OllyDBG and a bunch of other things on there and you're poking around with malware, because the malware is just going to go, well, hang on a minute, this is definitely an analyst machine even though it's not a VM, and then start doing weird things again. So disk indicators. A lot of these are quite common. So is the disk less than 200 gig? If it is, it's probably a VM, because nobody has a disk that's less than 200 gig these days. If you do, then you live in the 90s. Do the disk labels match known analysis machines? So if you pop an analysis machine or you upload something to like VirusTotal, or wherever, your malware runs and then it goes, oh, what's the disk label? And then it reports it back to the bad guys, and the bad guys go, oh, okay, so when I see this disk label, I'm going to pretend to be somebody else and not be malware. Again, disk hardware, like the controllers and stuff. So VirtualBox, for example, has a virtual IDE and virtual SCSI, and also virtual SATA, I think, controllers, which are not real controllers. So you can send them weird, you can ask what controller they are, and they'll be like, oh yeah, I'm such and such controller. And you're like, yeah, that's because you're not a real controller, and I can identify that because you're the only person who's ever used this actual real controller, because this name of this controller doesn't exist in real life anywhere. Like, okay, there is a real one, so it'll be called like Intel or something or other, but there's no real hardware that actually uses that controller anymore, because it's a legacy piece of hardware. So if you see it, you know you're in a VM. You can also do things like sending it specific ATA commands, because like you can go, okay, well, if it was the real piece of hardware, it would support this ATA command. So you send it an ATA command and it goes, oh, I don't know how to do that. And you go, okay, so you're definitely virtual then, because the real hardware would know how to do that. Yeah, disk serial numbers as well, so you can ask the disk for its serial number, and if it comes back with one that you know is associated with a virtual machine or an analyst box, you can go, okay, you're an analyst then, so I'm going to act differently. Windows 8 has this really handy API that they stuck in kernel 32 called isNativeVHDBoot. And what that does is it tells you whether the operating system was booted from a VHD, which is a virtual hard drive for things like Hyper-V and Virtual PC. So that's a dead easy trick, it's brain dead, it just returns a 1 or a 0. And you go, okay, I am running in a VHD, so I know I'm a VM. Network indicators. So there are some network interface MAC addresses. The OUIs for particular virtual appliances are always the same. So you can just look at it and go, oh look, it's VirtualBox, because it starts with 080027. You can change it, most people don't. We'll talk a little bit more about the state of sort of anti-analysis later. There are some relatively comprehensive guides on how to make a VM not look like a VM. It's still nowhere near perfect though. Virtual NAT. Chances are, if your NAT IP range is 192.168.53.1, it's probably not a real router. It's probably a NAT set up by a VM. That's not always the case, but like a lot of the time they just set up stupid ranges on the NAT. Also, things like if you talk to the DHCP server, you can send like weird malformed packets and it still responds to it because it's a virtual NAT and not a real one. And things like how it handles particular sets of communications, like whether it will actually settle a NAT route for one thing over another. You can use that as a fingerprint tool. So you can go, okay, I'm going to send like these 3 packets, and then the server's going to send me back this one packet. Does that one packet come back through? Because did the NAT implementation recognise this as a legitimate connection? And that's one way to fingerprint it, because you can tell whether it's a VM or not sometimes. Another brain dead one. Does the IP match a known sandbox system? So somewhere like malware or Cuckoo or Anubis or something like that. So where you upload a piece of malware and it says, this is everything that this process did. And you go, well, what's the IP address? What's my IP address? So I just go and talk to some IP address checker, and it goes, oh, you're this IP address. You go, well, I know that's the IP address of Anubis, so I'm not going to run. Also, shared folders. Shared folders between VMs and the host are implemented in a variety of different ways. A lot of the time they're just implemented as network shares. And often the network share providers are fake. So they've got like either you'll try and do a DNS request and it'll come back and say, yeah, this is this IP for this host, and you can talk to it that way. But most of the time what happens is they put a networking provider into the guest OS, and it uses that to override the traffic so that it can just basically pass it back through and out using an alternative mechanism. So for example, the VirtualBox shared folders provider for doing shared folders across for VirtualBox is one way to check, and you can also try to enumerate shared folders in a UNC path like VBox SF. I'm mostly going to talk about VirtualBox because it's dead easy to dig into, because it's mostly open source and relatively easy to analyse, and their bug tracker is quite funny because you can go through and just find all the bugs in them and go, oh look, we can use that as an analyst tool. Anyway. Yeah, other hardware indicators. So the screen. So who here has ran a VM and then they've resized the VM and then they've gone into like the display properties and had a bit of a giggle because their display resolution is like 746 by 1911, and you're like, don't think anybody makes panels like that. So that's kind of obvious, because like if it's less than 1024 by 768, well, you're either running in the 90s again, or you've got a weird VM setup. And again, nobody makes 1730 pixel by 1143 pixel panels, because they don't exist. Mainboard manufacturer, so you can look up the WMI information, look at the, I think it's like called Win32 underscore baseboard or something like that, and it'll tell you the BIOS reported name of the motherboard and of a bunch of other stuff, and you can see if they look legit. A lot of the time they're just called things like VMware or VirtualBox board or whatever. Another thing that's really hard for them to fake is that almost every virtualization solution fakes a chipset and fakes a motherboard. So you can say, is it running the i440FX chipset? Well, it's probably VirtualBox, because nobody has an i440FX chipset anymore because it's not 1994. And they're the only guys who use it, so it's the only one that they can emulate. It doesn't. It's PIIX3 is the Southbridge. So you'll often see that referenced when talking about VirtualBox, because again, nobody uses it for real hardware anymore. So the Intel 82371SB, also known as PIIX3, is the only Southbridge that VirtualBox can use. So if you enumerate the hardware and you find out that it's running that, you're pretty sure that it's running in a VM. The other one is can't talk to SM bus devices. So SM bus is the hardware bus that sits on the motherboard and allows you to communicate with onboard peripherals. So for example, temperature sensors, fan speed sensors, things like that. But also SPD chips on the RAM. So SPD tells you things like what frequency your RAM's running at, what banks are populated, what the name of, what the manufacturer and the model number is for individual RAM sticks. You're probably seeing this through tools like CPU-Z. So if any of you do any overclocking or things like that, you might have used tools like that to see what's running in there. The important thing is that you have to query that through an SM bus driver, because often what will happen is it'll The motherboard will pass that information to the BIOS, and the BIOS will expose that on the system, and that's easy to fake. What's hard to fake is real SN bus interactions. So if you attempt to do that and you don't see any SN bus devices and you can't talk to the SPD, then you almost certainly know that you're running in a VM, or you're running on a really weird old laptop that just doesn't support communications. But again, most of the time, it's going to be a VM. More hardware. My favourite thing in the world, CPU extensions. So SSE 4 is relatively new. There's also another extension called AVX. Look, there is. And also AVX 512 is a brand new one, which I don't think is actually implemented in any real processors as yet. But the thing is, most VM solutions don't actually pass these instructions through for various reasons, mostly just because it's quite hard to deal with. They can do it a lot of the time, but it's classed as experimental because they just can't test everything. So it's really hard for them to go, here's a new extension, we're sure it works. Because a lot of the time they're doing binary translation of instructions in real time. So if they get the translation wrong, you can run into certain bugs, and we'll talk about those later. But safe to say that QEMU was somewhat vulnerable to dodgy instructions getting, basically mangling it up and causing it all sorts of problems like remote code execution. But yeah, so essentially, like VirtualBox has an option where you can set the VM to enable experimental SSE 4.1, 4.2 pass-through. Without that enabled, what happens is the CPU, the virtualized CPU says, yeah, I totally support SSE 4.1 and 4.2, and then you try and use it, and it says invalid instruction. So you can guess quite easily that that's a VM when that happens. Some CPUs do implement only subsets of 4.1 and 4.2, but then you can just fingerprint which CPU it says it is. If it doesn't match up with experimental results, then you know it's a VM because, again, it doesn't match up with the real hardware. Same with AVX. Modern features missing. So VMs lag behind in terms of like hardware feature support. So things like UEFI. Most people support UEFI these days on their boards. Again, you can interrogate which motherboard it's running and say, well, that supports UEFI, why do you not have UEFI on? If it's got no support for it, then it's not going to work in the VM, and you're going to know that it's probably a VM. APIC, which is Advanced Programmable Interrupt Controller. Most VMs support that now. Some of them have it as an option to switch on. I don't think I know of any hardware that doesn't have it by default and have it enabled. So if you can tell that there's no APIC support, then you can usually go, it's a VM. HPET, high performance event timers. There's some fun stuff with that. I was chatting to a few of you before this about it. Yeah, HPET is, it's, so event timer, there's been a whole bunch of hardware event timers in the history of IBM compatible PCs and that kind of section of hardware. And the idea is that you can, depending on how they're actually set up, the idea is you can say, I'd like to start a timer and then in X many milliseconds or microseconds or nanoseconds, I'd like you to stop that timer and then raise an interrupt. Or you can just say, carry on going and I will read from you every so often and I want a really accurate timestamp. So, yeah, the HPET is one of these like fire, let it run, read a timestamp out of it every so often kind of deals. It's really, really useful for animation stuff. So like Windows 10, if you turn HPET off, the display runs like ass. Like you check when you like restore and minimize Windows, it'll like glitch out all over the place. It'll look awful. And the idea is that HPET can be really useful for timing that kind of stuff. If you find out that you've got no HPET support, you're either running really, really old hardware or it's a VM. Alternatively, there's a bug in VirtualBox that goes back from 4.3.8 going all the way back to the year 0, which was when they added HPET support, which you can manually turn on or off. If you turn it on, and the processor is an Intel processor with SpeedStep, which is most of them. SpeedStep, what that does is it allows your base clock multiplier to drop down so that you're not running at like your full frequency. So you might have, for example, you might be running 3 gigahertz full blast, and then it drops down to 1 gigahertz while you're idling. So the idea is it's using less energy. So obviously it's great for laptops and things like that, but it's also great for desktops because you're saving your energy. The problem is when speed step drops down and when the VM is idle, HPET wasn't properly updated, and the way that the emulation for it in VMs, for VirtualBox at least, was set up, it meant that it went backwards. So you would measure a timestamp, and then you would measure another timestamp, and the timestamp says, it was this time, and then it says, it was this time minus 10 seconds. And you're like, hang on a minute, it's gone 10 seconds back in time. How does that work? And there's a whole thread on this in their bug tracker, and it's quite amusing because people were literally just taking query performance timers and dumping the results and just seeing them go backwards. So the time was literally flowing backwards in HPET, which is a great way to identify that you're running in a VM because it never runs backwards in real hardware. Well, not outside, not in like Euclidean space anyway. TPM, again, most things have a TPM, most laptops do. Some don't. Budget stuff doesn't. But if you can see that there's a TPM there, so for example the ACPI table for TPMs is available, and you can't talk to the TPM, you've got a good idea that something fishy is going on. SLIC and MSDN. So who knows what SLIC is? Ooh, one guy. One guy has dealt with Windows licensing. SLIC is the hardware licensing lock that Microsoft can put, well, not Microsoft, but usually OEMs put into the UEFI to say, when you install Windows on this machine, look in the ACPI tables, see if you've got an SLIC and an MSDN section in there. If you have, use that as a license. So it's a hardware lock license. So you, instead of having to type in a key, it goes, oh look, this laptop's licensed, and just installs. So that's quite common. If you're running on an OEM laptop, if you've got an OEM edition of Windows installed, and you don't have an SLIC, you can start scratching your head and go, is this really real hardware? It's probably a VM. Most of the time, VMs don't pass that through. You can set that up. There is an option to pass custom binary ACPI table through VirtualBox. I think you can do it in VMware as well. But most people don't, unless they're building like a hardened anti-detection VM or whatever. But as I say, that's not something that most people do. Also, particular modern ports. So, if you've got a modern laptop, it's not got USB 3 support, start scratching your head, because again, probably a VM. So, I've talked a bit about ACPI. So this is what I talked about at DC 4420, if you were there. Probably none of you were. Basically, the ACPI is a set of tables, configuration data tables that are passed from the hardware, or more precisely the firmware, to the operating system so that they can understand things like how the PCI bus is laid out, information about support for HPET, information about support for SLIC, all sorts of different stuff in there. We'll have a look at that in a minute. So Windows exposes it to like user level. You don't need to be privileged to look at the data that's in there. There's 2 APIs that are listed there. Just go wild. In Linux, /sys has it in there. I can't remember exactly the path. Me and Don Spill, wherever he is, took a look into that a while back, and he was quite helpful with that. And you don't need to be root, and you don't need admin access. So yeah, you can do feature detection. So you can look for APIC, you can look for DMA remapping, DSDT and SSDT. Can't remember exactly what they are. HPET, PCI layout, SLIC and MSDM licensing stuff, TPM and UEFI, so all of the support for that kind of thing is in there. You can also start to look at the contents of those tables, and a lot of the time is in VMs, because they're fake, they just have words like VirtualBox in them. So, I don't know whether you can actually see that very well, but this is output from a tool called Firmware Tables View by Nersoft. That dumps out the ACPI tables. So you've got the contents of the SM BIOS, which is just the BIOS image. You've got the APIC table, SF, BATB, blah, 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 DMAR, which is the DMA remapping. You've got MSDM and SSDT, SLIC, UEFI, all of that good stuff. So yeah, so we can see that the OEM ID is Lenovo because it's run off a Lenovo laptop. So we know that the OEM for this is Lenovo, so it's probably a real piece of hardware. Then we can also take a look at the bottom, and in the SN BIOS we can see Intel Core i7 blah 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 blah. Looks like legit data. Virtualization Securi-Tay. Okay, so now comes the bit where I don't know whether this is going to work. But I'm going to give it a go. So, oh, that's actually quite big. Can you guys see that? Reasonably? Okay, right, so this is VirtualBox. So as you can see here, OEM ID is VBox. And the table IDs are like VBox APEC, VBox BIOS, VBox FACP. So these are kind of obvious, and also there's not that many of them because they're all virtualized. So this is the SN BIOS image for a VMware box, and it says Innotech GmbH VirtualBox a lot. And then it says it's a Pentium 3. This is a relatively new laptop, I'm pretty sure it's not a Pentium 3. I had a Pentium 3 laptop in like 1999. It was a brick. So yeah, so this is kind of obvious because it says VirtualBox in the bloody data. So yeah, that kind of gives the game away. You can fake this. You can supply a fake binary blob as an ACPI table. However, from the support forums, it sounds like things crash a lot when you do that because it thinks, oh look, it's got HPET support, and then HPET support isn't enabled, and then the system goes, and just falls over. Because nobody's ever really run into the corner case where the BIOS says, yeah, sure, it's got HPET, and then HPET doesn't actually really exist. Excuse me. Oh, dear. Wow, that was actually remarkably smooth. Oh yeah, I'm going to put this in here just in case you couldn't see it. So yeah, there's not much in there. You can see VBox is in like most of the names, and then you can see VirtualBox in the data. So yeah, so VBox Manage has options to put the faked ACPI tables in. It's primarily used to do the SLIC pass-through, so if you've got SLIC that's in the physical hardware and you want to license a VM instead of the physical hardware, you can pass through the SLIC data from the table, and the actual underlying virtual machine will respect the SLIC that's in there. So you can license whatever's inside. But you can also use it to trick vendor installers. So for example, there's a lot of server software that won't run apart from on the very specific piece of hardware that it was designed for. So like you get some HP server and then you'll get some HP software and it will only run on the HP server. So if you pass through stuff through a VM, because the VM will go, oh, well, I'm not a HP server because I'm a VM. So it won't install. So you can also use that as a trick to get around that. And yeah, it works until you actually try to use the advertised features, because you can't talk to SMBus and you can't talk to the hardware that you thought was there. So moving on to looking at the actual guest VM. The registry on that guest VM will have certain artifacts that will give away the game. Vendor-specific keys, so stuff that's set up for VirtualBox, VMware, Hyper-V, whatever. They set it for stuff like the guest packages, the guest drivers, things like that. Install software like analysis tools, again, they leave registry keys. And the Windows install date, for some reason, a lot of analyst machines set it to 1999, which is just really confusing because if it says 1999, it's obviously a VM. There is a better check. Did the version of Windows that's running on this system come out after the install date? Because if that's the case, something fishy is going on. Also, known install IDs and serial numbers. Now, again, a really common check, and most people sort of know about that by now and patched it. Driver indicators. So, VMs don't use normal drivers because the hardware that they've got is virtualized, so it doesn't act normally. If you've ever tried to use the VirtualBox graphics drivers with accelerated 3D, you all know how much of a pain they are. So yeah, you've got video drivers, sound drivers, printer drivers, all sorts of crazy stuff. So even mouse and keyboard have to be virtualized because obviously you don't always have focus on the VM, which means that sometimes it has to handle weird cases that you just normally would never have to worry about with real hardware. So you can look at the running driver list, you can look at the file system for the driver files or like the running driver service. You can look for utilities. So for example, VirtualBox has a bunch of utilities that are used for the networking stuff. You can identify them on the disk. You can just look to see if they're running. You can look for the DLLs on disk, blah, 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 blah. You can start digging around in the files for custom drivers, see if they respond to any that real drivers wouldn't. So that way, that's another way to fingerprint. So you can say, even if they change the name of the driver, I can work out that they respond to these 10 IOCTLs that no other mouse driver actually does, and you can identify it that way. So that's what's fun. It does require more work, but anyway. Object indicators. So the Windows object namespace contains things like mutexes, semaphores, events, all sorts of stuff that you wouldn't see on the file system, but are named objects that multiple processors want to access. So things like drivers, certain file system mount points are all just objects in the object namespace. You can look at what a process has open, so handles to which objects. You could look for specific objects by name, so you could say, well, when the VirtualBox shared folder driver is running, it creates this event. And if this event is there, then obviously the VirtualBox driver is running, which means I'm running in a VM. So yeah, so that's a nice little cheap trick. So even if the process or like the driver that has a handle to these objects is hidden by a rootkit, so say for example you enumerate through the list of running processors and a rootkit in the background takes the eProcess list from the kernel and chops off the process that you actually want to find, you enumerate through, you don't see the process, you go, oh great, there's no VirtualBox process running. That's awesome, I'm not running in a VM. However, if you then go and look for things like, is this object here? Well, the object is still there, it still exists, even though the process has been hidden. So even if you've got a rootkit that hides the process, you can still spot that sort of thing from Windows objects. You can also write a rootkit that hides those as well, of course. It's just, it's more work. Event indicators. Nobody does this. They should. If you want to see if you're running in a VM, or that if analyst tools were ever installed, look through the Windows event log, because nobody ever clears it. So when I install Visual Studio, it creates an absolute shit ton of events. It says, I'm going to install. Now I'm installing. Now I've finished installing. Now I've finished creating a system restore point. Blah, 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 blah. Here's all the service packs I'm installing. And you go, okay, so you've hidden that, but now I can just look back through the events and see that you did that. Or when you first set up the VM, you put the tools on there, so like the guest tools on, so you could resize it to a nice resolution so that when you were installing the tools, it wasn't a massive pain in the arse, and so that you could file copy in and out, and then you removed them. But you left the event logs behind, so I can see that you did that. So nobody does that for some reason. You should, it's cool. You can also check for things like real hardware, when you turn it on and turn it off and suspend it, creates different logs to when you do the same thing with a VM, just simply because of the way the power management works on a virtual system. So when you look at the event IDs and you look at the event data and stuff, it's just different. It's not really obvious to show in a slide, but it is just different. And if you have to dig around, you can see how it's different, because it's just like the timing and stuff is a bit weird. Instruction indicators. So we talked a little bit before about SC 4.1, 4.2 and AVX as extensions. There are other ways using instructions that you can sort of dig around and work out if you're running in a VM, or running in an emulator. So for example, can you? So virtualization solutions don't create a perfect representation of the instructions that's running on the system. This is just a thing that VMs don't do. They can't, because it's just not real hardware. And you need, so for example, let's say I want to write to a particular block of hardware memory that's related to the shared system memory between my graphics card and my processor, because the main system memory has to obviously store some sort of frame buffer so that the processor can go, oh, let's draw something in this frame buffer, and then that can be copied out to the graphics card. Or you can use a memory hole to do the same sort of thing. But you can't do that in a VM directly, because if you could, then you would just be able to overwrite the screen regardless of whether you were, regardless of whether you're looking at the VM or not the VM. It could just go and read the display buffer from outside of the VM, and that'd be awful, because then it would be able to read your screen. As in, not the screen of the VM, but if the rest of the screen of the real system, and then that would be really obvious that you're running a VM. So, if the CPU could do that, if the virtual CPU could do that, that'd be awful. It could just absolutely screw with everything. If you've got a host system running 10 VMs, they could read and write over each other, and it'd be just terrible. So instead, they have to be virtualized and separated out. So many extensions aren't available or are faked. We talked about that. RD-RAND and AES support are again two that commonly just don't get exposed to VMs. RD-RAND particularly because there are concerns about, what happens if a VM uses RD-RAND in a weird way and messes with the entropy and blah, blah, blah. This is security decisions by people who don't understand hardware random number generators. So you can check if the CPU has the features, and then check if the features are really there. VM-specific opcodes, so these are great. So the way that VirtualBox actually, well, I don't know that it still does. The way that VirtualBox used to do copy-paste sharing, you could basically copy something into the clipboard, and what would happen was it would actually emit an opcode that didn't exist. It's not a real instruction on the hardware, and it would generate a invalid opcode exception on the CPU. And the virtual machine would catch that exception and go, oh, I recognise that opcode. That means he wants to copy from the clipboard inside the machine to the clipboard outside the machine. So it would run that, and it would carry on. And it would swallow that exception. It would swallow the invalid opcode exception. So what you would do is you would run a piece of malware that tries to run that instruction, and then suddenly you don't get an exception. So you know you're in a VM. There's lots of different little ones. There's basically anything where there's some sort of interaction between the host and guest. Most of the time you can guess that it's either going to use faked opcodes, or it's going to use the in and out instructions and do some weird stuff with that, which again you can use as a... Oh, are you joking? Your device will restart at 1855. Thank you, Windows. Sorry, 1655. I've got 15 minutes. Thanks, Windows. Thanks, Microsoft. I love you. Poor implementation can very much lead to outing yourself. So, for example, the VMware COM channel stuff, these in-out instructions, you can just basically call those and see what happens. Normally, you would get some jargon back. In this case, it just would do something completely different. The mod RM emulation bug from Fistful of Red Pills, which is a talk/paper from some guys, I can't remember who. That one was fun because basically what happened was the mod instruction wasn't understood properly, so you could actually encode a set of parameters for mod, and it would say, oh yeah, that's fine, and then it would crash. It would actually crash QEMU and just, it might have been KVM, I can't remember. The ICP-BP instruction, that used to crash QEMU. Tavis Ormandy found that one, and particular encodings of the AAM instruction as well used to crash QEMU. So emulators are often a little bit more fragile because you can generally just crash them if they get it wrong. Bugs. Digging through the VirtualBox bug tracker. So yeah, 4.3.18, the results from query performance counter would go backwards. I talked about this before. So you can go back in time and then work out, oh look, it's back in time. There's an ongoing bug in the 4.x branch which causes the hardware AT timer, which is not HPET, it's similar to HPET, but it works in a different way, to lag and skip when the VM is idle and speed steps enabled, which is another speed step problem. Easy to detect because you monitor the QPC output, and what happens is it will go 1 second, 2 seconds, 3 seconds, 12 seconds, 13 seconds, 14 seconds, 19 seconds. So there'll just be a big gap between the measurements. Debug registers 5 and 6 get zeroed on every context switch from host to VM. Again, that's an ongoing one. So basically you would put some values in the debug registers. wait for a context switch, see if the debug values are still there when it comes back, and if they're not, then you know you're in a VM. Sending packets with an MTU so, larger than 2 kilobytes and setting a don't fragment flag. If you've got a bridged adapter, that breaks the bridged adapter in VirtualBox. It doesn't understand how to do that, so the packet goes out and hits the remote server. Let's say, for example, you put an ICMP echo request in there, a big one with a large MTU. You send that packet out. It will hit the remote server. It won't come back. It won't be able to actually receive that packet back. It just doesn't understand how. And many, many more. So that's fun. That happens sometimes. So sometimes you'll do something like, for example, sending a packet that the network stack doesn't like, and it will just crash the driver. And that's pretty obvious that you're running in a VM if it crashes with the VirtualBox driver, because, you know, it's slightly disruptive though. I think an analyst might know this, unless they're particularly dumb. Yeah, so VMs, it's pretty easy to notice that you're in a VM. It's pretty hard to fake that you're not in a VM. It's really hard to do a 100% copy. Sandboxes. And I mean stuff like Sandboxy, not like the Chrome sandbox. Again, this is more of an on-system method of encapsulating things. So you've got to get down and dirty with the real processor. You've got to dig into it. You've got to hook it. You've got to do things that where it might be able to notice that you're there. So it's a little bit easier to spot these guys. So debugging, hooking, there's some specific solutions like Sandboxy and whatever. And then there are generic indicators that you can use just to see if you're in a sandbox. Debugging checks, so these are all understood in common. Weak source, because they don't really just detect the sandboxes, they detect debugging. Not really going to talk about this, it's been done to death. Hooking detection, so hooks redirect the code to alternative routines. So the idea is that I go to call this API, instead of calling that API, I call some other function which messes with the results of the real API and then gives me garbage data back. You can also do it system-wide with SSDT hooks, IDT hooks, redirecting the NT functions. Again, I'm not really going to talk about that. There's also supported stuff like filter drivers and callbacks, which again can be used in weird and malicious ways, but again, I'm not really going to talk about that. Detecting detours. So normal functions start with a mov EDI EDI, which is a 2-byte not, which means it does nothing. It moves the value of the EDI register into the EDI register, which means it does nothing. The normal function has 5 null bytes before this. This is when compiled with a Microsoft compiler, because this actually supports detours. And the idea is that you can put a jump -5 in the mov EDI EDI, because it's a 2-byte instruction, and then put another jump somewhere in that those 5 bytes before. So when you call the function, instead of doing mov EDI EDI and then going into creating a stack frame, instead what happens is it jumps backwards 5 bytes and then jumps somewhere completely different. And that way you've detoured the call. You can also use load library and get proc address to find the pointer to the API, then find a bunch of other APIs that are inside the same module and work out whether the one that you were trying to call, the target, was in... Sorry, I'm reading the entire wrong thing. Read the data at that function and work out whether the data matches, so whether there is that 5 bytes of null and whether that mov EDI EDI is there. Sorry, I was talking about something else. Pointer modification, here we go. Basically, a lot of the time when people change like a pointer somewhere, so for example, the hook get proc address, so you go get proc address on this particular function, I want to know what the address of this function is, and they'll return a completely different address somewhere completely different, so that when you try and execute that, you're executing a completely different section of code. So what you can do is you can go, okay, how big is the code section for this library? So was the pointer you gave me inside that code section? If not, probably sketchy. But again, this is mostly anti-debug stuff, and I'm just going to very quickly skip over this. Sandboxy. That's easy. You just say, is this module loaded? If it is, oh look, Sandboxy. So that's easy. Wine. Does kernel 32 have that function in it? If it does, I'm in wine. So these guys make it really easy. So is my stdio redirected? So it's my standard input or output redirected. A lot of the time when things are doing like monitoring of your process and dumping it for a report, they're going to want to know what comes out of standard out. So they redirect it. Is my parent process explorer.exe? Am I running a different user to my parent process? Am I running as part of a job? So a job is a Windows sort of structure where you can group multiple processes together. And the idea is that if the owner of the job gets killed, it kills all the child processes. It's useful for debuggers because you can have 10 processes running, all that are sat under the same debug session. You kill the debugger, all of those processes end. So if you're debugging a process, it's probably in the job. So you can identify it that way. OllyDbg is identifiable that way. So sandboxes are relatively easy. Once you actually get in the mud with the malware, it's relatively easy just for it to go, you're right there, I'm looking at you. Yeah, rootkits are generally necessary to stop you from being identified, but again, you're working against the operating system at this point, and it becomes quite difficult. Behavioral detection. So a VM that an analyst uses isn't the same as the PC that your mum uses, or whatever. Like, you're not physically interacting with it in the same way. You're not using it to do the sort of thing that normal people use a computer to do. You're not. You possibly don't have access to mobile sensors, because if you're virtualized and it's a mobile device, for example, Microsoft Surface, if you're running Windows on it, well, that's an option. What if it's Android malware? It should be able to talk to the mobile sensors. If it can't see that the mobile sensors are doing something normal, like, for example, the accelerometer in it is showing that you're walking, or the gyroscope or the magnetometer aren't giving you normal values, you know it's probably fake. Looking for a pattern of use. So, for example, you want to look for hotspots. So a screen like a Windows desktop, you've got the start button, bottom left. You've got the close button, top right. You've got these points that you're always clicking on, and your back and forward buttons on a browser. You're sort of always hitting these hotspots. If you're just randomly setting where the mouse goes, then it's not going to look like that. So yeah, so mouse indicators. Is the mouse moving? Common trick. Look for hotspots, match. Click and drag. Almost no fake mouse mover things actually click and drag anything. You click and drag all the time. You resize windows, you move them around. People never do it. Silly. Browser indications. An analyst is not browsing the internet. An analyst is not a normal person. Their VM is not for their general use. They're not going on Reddit. They're not going on Twitter. They're not going on Hotmail, Office 365. They're not, looking around on the Daily Mail like idiots. They don't have bookmarks. They don't have plugins. It doesn't look like a normal user. These browsers are fake. They're not being used like a normal person would use them. Mobile sensors, as I mentioned before, PCs aren't the only platform. Mobile things move. Mobile things are interacted with in a different way. You make a call on your phone. You put your phone next to your face, and hopefully you don't face dial people, because there's a proximity sensor in there that says it's next to my face. So if that proximity sensor never says anything's next to it, then it's probably not a real phone. If your phone is not moving, I'm moving my phone. It should be pretty obvious that I'm moving my phone, even when I've got it in my pocket. The accelerometer is going to be showing that as I walk, my leg is moving. The magnetometer is going to be picking up weird things because I'm stood next to a speaker or something. All of these things are going to be real values that you should be able to read, but if you can't read them, it's probably not a real mobile device. Call history, text history, and contacts list as well. That's all important to know about. So here's this legally sketchy bit, and I really hope my laptop doesn't shut down in the middle of this. On the one hand, online scanners and sandboxes invite you to upload malicious stuff to them. On the other hand, they probably don't want that malicious stuff actively targeting them and reading their data and stealing all of their analysis software. Consult your lawyer if incarceration persists for more than 4 hours. Or your physician. I don't mind. So offensive measures. So sites like Cuckoo, Malware, Anubis, they're sandbox services that you upload a piece of malware to, and it says it read these files, it read these registry keys, it did this communication with this server at this time, blah, 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 blah. Here's all the activity it did. It spawned these processes, it dropped these files. So you could upload something to it that starts looking into that kind of thing. So you can't, why dry run it when you can do it live? Because it's illegal. So, well, it may be illegal, I don't know. I'm not a lawyer. So, yeah, you don't want to really have data exfiltrated to a live host because then that live host becomes known as a dodgy malware site, and you know, I don't really like my domain with my whois information saying malware. So standard out is often printed, but it's limited in length because that way you could just go, hi, here's all of the processes that are running, and here's the contents of this file, and it would just tell me in the report, which would be bad. So what else is in the report? File operations, registry access, DNS lookups, lots of static analysis stuff, but we don't really care about that bit. Idea is you want to cram as much data into that as possible, and the way you do that is by faking activity dynamically based on the contents of files, or the content, or what the piece of information you want to dump out of the system. So you can read lots of files, prefix the names with integer indices, and then have the file names be like base 64 encoded blobs of the file. So you can say, okay, I try to read blah 0001 underscore big load of file data dot text. Then I try to read blah underscore 002 next big block of text. And that way, once you take all of those file access results out of the report, and you stick them back together in the order from 001 to 999, the contents of those file names becomes the data that you actually just exfiltrated. So you can exfiltrate it in the file names, you can exfiltrate it in the registry key names that you try to access, blah, 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 blah. So the idea is you can then start dumping out things like their analysis software, and then you can start digging around in it. There's no POC for this because I didn't do it. And you shouldn't either, without express permission. So what do we want to dump? We want to dump the process list, the module list, contents of interesting files, registry keys that we're interested in. Again, back for those juicy indicators like what's the, I don't know, the serial number of the OS install or whatever. Yoink. An afternoon of messing around with simple code can get you the results that you actually want. You can basically look at all of the different common sandboxing and analysis systems online, get all of their on-system analysis data off, and then start digging through it, reverse engineer it. Damn it. I hate you, Windows. Trying to remember what's in the rest of my presentation now. So yeah, it's almost near the end. You can start digging around in that kind of thing, and you can start identifying what's broken, what's not broken, where it looks, where it doesn't look. You can start identifying how it gets that report data off the guest system and onto the host, so it can report it back to you. That's pretty important because if you can start subverting that, you can lie in the report, which means that if you infect the virtual machine that was meant to be analysing you and then get the results to say something completely different, you can pretend that you weren't malware in the first place, which is pretty much the ultimate goal of what it wants to do, what malware would want to do. What else am I talking about? Damn it, Windows. Ruining everything. So, yeah, you can steal that stuff and it's fine. You can tell I didn't practice this. Thankfully, it's not asking for my password on boot up again. No, so I'm pretty much almost done, I think. I don't think I've missed anything off the end of this, I hope. But yeah, so the general idea is that the more information you can steal off of those systems, the more likely it is that your piece of dodgy software is not going to be identified as malware, and that's essentially the goal, or rather the goal of the bad guys, and we want to understand how they do that. Yeah, I think I might just leave it there and say any questions, because I think I had like 2 more slides. So my apologies for Windows being terrible and rebooting. I will freely admit that. I'm sure I'm going to get ribbed about that at work. Shut up, Aaron. Any questions?